What happens when two of the greatest minds in history independently invent the same tool, one capable of explaining falling bodies, the motion of planets, and the behavior of the universe itself? What happens when that tool, calculus, stops being a mathematical idea and becomes a symbol of national prestige, scientific identity, and intellectual power? Today, you're about to see how a formula, a symbol, and a method for studying the infinitely small ignited one of the fiercest, quietest, and deepest wars in the history of science. This is the story of Isaac Newton and Gottfried Wilhelm Leibniz. Welcome to Newton versus Leibniz, the war for calculus. On one side stands Isaac Newton. He is born in 1642 in Woolsthorpe, England, in the middle of a civil war. He arrives prematurely, tiny, fragile, so weak that no one expects him to survive the night. But he does. And behind that frail body emerges a colossal mind. Newton grows up in silence, shaped by the early abandonment of his mother and an extreme emotional sensitivity. From a young age, his intelligence is unsettling. He builds mechanical models, studies classical geometry, experiments with light, and spends endless hours writing notes he never shows to anyone. He is a physicist, mathematician, astronomer, alchemist, and theologian. Newton works alone, always alone, with an almost supernatural discipline. He distrusts his peers. He is horrified by criticism. He believes knowledge must be refined in secrecy before being shown to the world. He represents isolated genius, the power of a solitary intellect advancing in silence. His essence could be summed up like this: truth reveals itself to those who work in the shadows. On the other side stands Gottfried Wilhelm Leibniz. He is born in 1646 in Leipzig, in a completely different environment. His family lives surrounded by books, languages, and philosophy. Leibniz learns Latin before the age of 12, studies law, logic, and metaphysics, and by his early 20s is already writing ambitious intellectual treatises. Unlike Newton, who withdraws inward, Leibniz opens outward. He travels, he converses. Debate is how he thinks. He speaks with kings, ambassadors, scientists, and philosophers. He is an inventor, historian, diplomat, engineer, and mathematician. He believes knowledge must be shared, that science advances when ideas circulate. He represents the connective, expansive, elegant mind. Leibniz dreams of creating a universal language capable of expressing any thought. His philosophy is simple and clear. Ideas must be free. Two colossal minds, two opposing ways of seeing the world. One shared obsession, mastering the infinitely small. This is where the fight begins. The origin of the war begins in a dark moment. In 1665, the bubonic plague strikes England with full force. Cambridge closes, and Newton, just 22 years old, returns to Woolsthorpe, where he will live in isolation for more than a year. What would be a tragedy for most becomes an explosion of creativity for him. He conducts optical experiments, sketches the foundations of universal gravitation, and, without anyone knowing it, builds a new mathematical tool to describe change. He calls it the method of fluxions. His calculus allows him to measure instantaneous slopes, velocities at every point, areas under curves. It is the cornerstone of modern physics. But Newton makes a crucial decision. He does not publish it. He trusts no one. He believes the world is not ready. He prefers to keep his discovery locked away in private notebooks. Calculus exists, but invisible. While Newton works in isolation, Leibniz lives a completely different story. In 1672, he travels to Paris as a diplomat. There, he comes into contact with the most important mathematicians on the continent. He learns from Huygens, studies curves, infinite series, and advanced geometric problems. Between 1672 and 1676, he begins to construct a method for studying continuous change. He arrives at the core concepts of calculus, derivatives, and integrals. But Leibniz has something Newton does not: the urge to share. And in 1684, he publishes his Nova Methodus. He introduces an elegant, visual, intuitive notation. His way of writing calculus captivates Europe. Germany, France, Switzerland, and the Netherlands adopt it almost immediately. Calculus becomes a new European language. There is, however, a delicate point between Newton and Leibniz, a correspondence between 1672 and 1676. Newton sends some results, but never his full method. He never reveals his fluxions. Years later, these letters will be used as weapons, but for now, no one knows. By the end of the 17th century, calculus exists in two parallel worlds: Newton's, secret and profound, and Leibniz's, public and elegant. The question becomes inevitable: who really invented it? Tension rises. The collision is inevitable. The war officially begins in 1699. Nicolas Fatio de Duillier, a close associate of Newton, publicly accuses Leibniz of plagiarism. He presents no solid evidence, but in 17th century science, insinuations matter more than facts. Leibniz protests. He defends himself fiercely. He demands justice. But doubt has already been planted. In 1703, Newton becomes president of the Royal Society, and everything changes. From silent genius, he becomes the most powerful man in English science. He controls committees, publications, decisions, and reputations. He becomes an institution. Leibniz, naively trusting in impartiality, makes a fatal mistake. He asks the Royal Society to conduct a formal investigation to clear his name. Without realizing it, he hands his enemy the weapon. The Royal Society appoints an independent committee. But independence is an illusion. Newton controls the sources. Newton decides which letters are included. Newton interprets dates. Newton defines the conclusions. Worst of all, Newton himself writes parts of the final report. In 1712, the Commercium Epistolicum is published. Its verdict is clear. Newton invented calculus first. Leibniz came later, and his work was influenced by the Englishman. The word plagiarism is never used, but the message is unmistakable. It is a public sentence, a scientific humiliation. Leibniz's reputation collapses in England. The continent defends him, but without the institutional power Newton commands. Leibniz spends his final years isolated, ill, and bitter. He dies in 1716 almost alone, without honors, without recognition. Not even the Berlin Academy of Sciences, which he himself founded, sends representatives to his funeral. Newton, meanwhile, grows old as president of the Royal Society, respected, feared, untouchable. The war seems to have a winner, but history has not yet delivered its true verdict. Centuries later, historians and mathematicians return to the conflict with something Newton and Leibniz never had: perspective. With access to complete notebooks, full correspondence, and impartial analysis, they reconstruct the truth using modern historical rigor. The conclusion is clear. 1. Newton arrived first. His notebooks from 1665 to 1666 contain fundamental ideas of differential calculus. Chronological priority belongs to him. 2. Leibniz arrived independently. His manuscripts show a separate development. He needed to copy nothing. There is no evidence of plagiarism. 3. Modern notation belongs to Leibniz. His symbolic clarity was decisive. 4. England lost a century of progress. Clinging to Newton's geometric methods out of national pride delayed British mathematics for nearly 100 years. 5. Modern calculus is the child of both. Newton laid the foundations. Leibniz built the language. Two geniuses locked in conflict over the same idea. Two temperaments destined to collide. A war that shaped centuries of science. This is how Newton versus Leibniz, the war for calculus, comes to an end. This was Versus, where history becomes battle,